Hey everyone, and welcome back to The Explainer. Today we're taking a really high-energy tour through what I like to call the ultimate engineer's toolkit. We're going to uncover the hidden mechanical gatekeepers of our modern infrastructure. So we're talking about valves in gas transmission and distribution systems. These are the completely unsung heroes operating silently all around us every single day, and today we're finally putting them right in the spotlight.
So just think about this for a second. How do you safely control a highly pressurized, completely flammable fluid that's traveling across literally thousands of miles? I mean, we're not talking about your average backyard garden hose here, right? We're dealing with raw natural gas under immense, highly volatile pressure. It's just a massive logistical and, frankly, terrifying safety problem. You obviously can't just flip a standard switch to turn it off. You need a very specific set of mechanical heroes to keep everything flowing smoothly and, well, keep us from facing a catastrophic disaster.
Okay, let's dive into it. To actually tame all that pressure, we need to start with the absolute basics. At its core, a valve is simply a mechanical device that controls, regulates, or stops fluid flow in a pipeline. Now, I know that sounds super simple on paper, but out in the field, in the gas industry, these devices are incredibly complex. They are highly engineered pieces of equipment that make modern energy transportation even possible in the first place.
In practice, these things act kind of like the ultimate directors of heavy-duty traffic. Their to-do list is huge. They're tasked with isolating pipelines, regulating flow, preventing backflow, triggering emergency shutdowns, relieving pressure, and even balancing massive system networks. Choosing the exact right valve for the exact right job is absolutely crucial. The properties of the fluid and the specific operating conditions dictate pretty much everything. But above all else, having rock-solid sealing performance is the main thing preventing a really dangerous gas leak.
So let's actually meet the lineup, shall we? First up is the ball valve. And the secret to this one is exactly what it sounds like. It uses a rotating ball with a central opening. When that opening lines up with the pipe, boom, gas flows. Then you just give it a quick 90-degree turn, honestly, kind of like turning the deadbolt on your front door, and it fully closes. Because of that specific design, you get a super tight shutoff, incredibly quick operation, and almost zero pressure loss. You're going to see these everywhere, from your standard gas pipelines right up to massive LNG facilities and emergency shutdown systems.
But okay, what if you're dealing with a gigantic transmission line and you need the absolute minimum resistance possible? Enter the gate valve. So instead of a rotating ball, this guy uses a gate-shaped disc that moves vertically. Think of it almost like a medieval portcullis or even a guillotine. When it opens, that gate lifts completely out of the flow path, and that is huge. It means there is virtually zero resistance to the gas moving through, which translates to minimal pressure loss. That makes the gate valve perfectly suited for massive transmission lines where you just need simple, reliable on-off service.
Now, this actually sets up a classic engineer's dilemma. On the one hand, you've got the massive gate valve, which gives you that incredibly low pressure loss. But what if you're stuck on a cramped offshore platform where you literally have zero extra space? Well, that's where the butterfly valve really shines. It uses a rotating disc to control the flow, making it compact, lightweight, and capable of lightning-fast actuation. So if you're the engineer designing a large diameter system, you're constantly having to weigh these options. Do you prioritize the absolute lowest pressure loss, or do you desperately need a fast, space-saving design?
Okay, but what happens when the fluid you're moving isn't just nice, clean gas, but something thick, messy, or highly corrosive? That's when you call in the plug valve. It features a rotating tapered plug inside, and its absolute superpower is creating an incredibly tight seal. So when you're dealing with harsh slurry service or highly acidic fluids, the plug valve steps right up to keep things locked down and completely sealed, no matter how nasty the conditions get.
And speaking of nasty fluids, we definitely cannot ignore the brilliant simplicity of the diaphragm valve. The whole secret here is a flexible rubber diaphragm that just pushes downward to stop the flow. Because of that incredibly clever design, the fluid never actually touches the moving metal parts of the valve. This sort of no-touch approach makes it incredibly corrosion-resistant and super easy to maintain. It's an absolute lifesaver in chemical processing systems where corrosive fluids are just running non-stop.
Now, up to this point, we've mostly been talking about what are essentially heavy-duty on and off switches. But what if you need, say, a dimmer switch? Well, that's the globe valve. It's not just about slamming the flow entirely on or entirely off, it's engineered for highly precise flow regulation. The internal disc moves gradually toward the valve seat so you can dial in low, medium, or high flow with incredible precision. If you're managing a really delicate process control system where the exact flow rate matters minute by minute, the globe valve is for sure your go-to mechanism.
So when you lay out all the options, you really start to see the ultimate engineering toolkit take shape. We've got the quick shutoff of the rotating ball valve, the massive isolation power of the vertical gate valve, the compact speed of the butterfly valve, the incredibly tough sealing of the plug, the brilliant corrosion resistance of the diaphragm, and finally the precise regulation of the globe. It's fascinating because every single fluid control problem in the gas industry has a highly specific mechanical solution ready to go.
And of course, these mechanical tools aren't just sitting around in a vacuum. They are deployed on a truly massive global scale. We are talking about gas transmission pipelines that literally span entire continents, modern LNG facilities, sprawling refineries, and remote offshore platforms. They all work together in this massive, synchronized network to connect incredibly complex industrial facilities all over the world. They are, quite literally, the joints and muscles of our global energy infrastructure.
But, it isn't always smooth operations. Let me ask you this. What actually happens during a critical pipeline emergency? Just imagine an unexpected gas leak on one of these massive transmission lines. Suddenly, the stakes are unimaginably high. Human lives and the surrounding environment are immediately on the line. You obviously can't wait for a technician to drive 50 miles out into the wilderness to manually turn a giant wrench. You need an immediate, automatic, system-wide response.
And honestly, this is where the true engineering significance of these valves shines through. Because it isn't just about moving gas from point A to point B. It is entirely about safety, reliability, and environmental protection. When a leak is detected, automatic valve closures instantly trigger an emergency shutdown. They immediately isolate the danger, managing that massive industrial risk and making sure our environment is protected from catastrophic fires or spills.
So the big takeaway here is simply this. Proper valve selection is what ensures safe operation, reliable performance, and efficient gas transportation. It's kind of incredible to think about, isn't it? Our modern lives rely completely on these hidden mechanical gatekeepers operating silently beneath our feet, deep down in the ocean and out across vast deserts. So the next time you effortlessly turn on your stove or switch on your heater, just think about the immense, pressurized power flowing right beneath you. What do you think would happen if even one of those thousands of silent, highly engineered gatekeepers just decided to take the day off? Thanks for joining me for this explainer. Keep wondering, and I'll catch you next time.